Let's dive into the world of flip-flops, sequential logic circuits that have memory. Today, we'll focus on the edge-triggered SR flip-flop implementation, an essential building block in digital electronics. So, what exactly is an SR flip-flop? It is a bistable sequential circuit that stores one bit of information. It has two control inputs, set and reset. The S or set input sets the output Q to 1, while the R, or reset, input resets the output Q to 0. Let's take a look at the truth table for an SR flip-flop. When both S and R are 0, the output Q remains unchanged, holding its previous state, thus acting as a memory. When S is 0 and R is 1, the flip-flop resets, setting the output Q to 0. If S is 1 and R is 0, the flip-flop sets, and the output Q becomes 1. Note that the case where both S and R are 1 is a forbidden state. This is because it can lead to a race condition, making the output unpredictable. Here, we will explore the difference between edge-triggered and level-triggered flip-flops. A level-triggered flip-flop, also known as a transparent latch, responds to the clock signal level, whether it's in a high or low state. On the other hand, an edge-triggered flip-flop, also known as a true flip-flop, responds only to the transition of the clock signal, specifically the rising or falling edge. This is a diagram of an edge-triggered SR flip-flop. It consists of two latches, a master latch and a slave latch. The clock input controls the state of these latches, ensuring that data changes occur only at the edge transition of the clock signal. As shown, the clock input is connected directly to the master latch, and through a NOT gate to the slave latch. The S and R inputs are fed into the master latch. The master latch passes its output to the slave latch, and the final output Q and Q' are taken from the slave latch. This master-slave configuration ensures that the flip-flop is only updated at the rising edge of the clock signal. Let's examine how the master-slave operation works in two phases. During phase 1, when the clock is high, the master latch is enabled while the slave latch is disabled. This means the input is passed to the master latch. In phase 2, when the clock is low, the master latch is disabled and the slave latch is enabled, and the data from the master latch is then passed to the final output. Edge-triggered SR flip-flops can be efficiently implemented using NAND gates. The master latch consists of two NAND gates where S1 equals S NAND CLK, and R1 equals R NAND CLK. Similarly, the slave latch consists of two NAND gates where Q equals S1 NAND Q', and Q' equals R1 NAND Q. The use of NAND gates is advantageous because they are universal gates, making them efficient for integrated circuit implementation. Edge-triggered SR flip-flops offer several key advantages. They eliminate race conditions and timing hazards, and they provide precise control over state changes at clock edges. Therefore, they form the foundation for synchronous digital systems. If you like this video, hit that like button and don't forget to subscribe. Visit CodeLucky.com for more such useful content.